Welcome, class, to the asynchronous portion of your lecture, joined by fully synchronized real-time students who are listening to the lecture, participating, and diligently taking notes, as you should also be during this lecture. Now, for some of our students, this will be a little bit of review, so they're going to seem fully trained in the topic. So this is for the week of February 11th, and the topic in the syllabus is energy and conservation of energy, and also friction and special relativity, all in one. So I think we may talk about friction in passing, but we're going to focus on energy and relativity. So, first of all, could I ask someone from the live audience to give your best definition of what energy is? Who wants to take a crack at it? Someone raise their hand. No takers? Okay. Okay, Nicholas.
The ability to do work.
Ah, very good. Perfect. Exact definition. Very good. Energy is the ability to do work. That is the definition of energy. So that means energy is not a substance, right? It is not a substance. It is not a force. Energy is also not coffee. Okay? Coffee of two F's? I can't spell up close. Okay. So that is what energy is and is not. So let's talk about what this means. So energy is the ability to do work. We all have an everyday understanding of what work is, but there is a very well-defined physics definition of what work is, which is very precise. Does anybody know that definition of what work is? What? Yes.
Is it the amount of force applied over distance?
Precisely. Okay, good. Watch. Here is a box. The box is on a floor, and there is friction present, so if I push the box, it'll go a little ways, but then stop. Oh wait, I've got a fun idea. Let's try it like this. I got a fun idea. This is going to be great. Here's my friction floor, and now somewhere, no, those are shapes. Are there shapes?
Yeah.
Where are they? Do we know? Hold on, folks. Hold on. Do we see shapes? Shape pen. Ah, we have it. Okay, let's try this. Oh, sorry, class. I don't get it. It's not working. Well, it was going to be great, but once again, technology is failing us. Hold on, let's try this. Wait a minute. Okay, let's pause. Okay, so work is force times distance. So work equals force times distance. And remember, both of these are, well, let's see. Distance, length is not a vector quantity. Okay, anyway, let's just do it that way. Work is force times distance. So if this man pushes this block across this floor, he's doing work. So let's say the distance from where the box starts to where it stops, the distance d equals 10 meters. And the force which he applies to the box equals 100, or let's say 1,000 newtons. Here we go. Push the box 10 meters. And so the work is going to be 1,000 times 10, which equals what? Someone from the live audience. 10,000. So 10 K, and who remembers the units of energy, Michael?
Joules.
Joules. I said energy, but let's just leave it at work for now. Joules. So 10 kilojoules. So that is how you quantify work. It's the force applied over a distance. Now, let's erase. Hold on, let's make a new sheet here. So let's do another example. Right now we're just finding work. So let's say you have a mass and you're going to raise that mass 10 meters. And let's say the mass equals 10 kilograms. So how many newtons of force would it take to begin lifting that mass? Yes. Not 10 newtons.
Or 10 joules, sorry.
Not 10 joules. Okay, let's take a look. Do a little review. So the force due to gravity equals mass times the gravitational constant. Or, I'm sorry, times the acceleration due to gravity on Earth. So G on the surface of the Earth always equals 9.8 meters per second, meters per second squared. So Fg equals 10 kilograms times 9.8, so it obviously equals 98 newtons. So you need a force bigger than 98 newtons to bring it up. If you apply exactly 98 newtons, it essentially becomes weightless. Okay? So let's say we accelerate it up with a force of 100 newtons. So the force up, sorry, my pen's a little messed up. So force up equals 100 newtons times 10 meters. So how many joules is that? 1,000 joules of work has been done. And you can all picture this in your own life. When you lift things, you do work, right? Your force times distance. All right. Now we will stop and go to the next lecture.